Something went wrong with the chat apparently. But yeah, we are live on YouTube.
Okay, then with that, I would say welcome to the third session, the last session of this year's WeSST Symposium group. I would again shortly introduce myself. My name is Norbert Bader. I'm a postdoctoral researcher currently still at Hannover University in Germany, studying highly loaded EHL contacts mostly. We have co-organized this symposium between three of us. There's Martina Stella, who is not with us yet. She is a postdoctoral researcher at ICTP Center in Trieste. She will join us later, and Michael, who I think will shortly introduce himself.
Hello everybody, I'm Michael Vorlaufer. I'm a postdoctoral researcher at the University of Vienna, and I'm doing high-throughput simulations for tribological systems.
Yeah, thanks. Before we start with the first talk, let's just think about the topic one more time. The topic of this year's seminar was Tribology, Applications of Big Data, High Throughput, Machine Learning, and Artificial Intelligence. We are now in the third session of the seminar, coming sort of to the closure of this topic. That means we started in the first session with very basic talks about big data. What possibilities does artificial intelligence actually show for further research in our topic? And in this topic today, this session, we will be more actually ending up at the point of really talking about tribology, tribological systems, and where these applications can help us. And with that, I want to already start with our first speaker. We are very happy that Dr. Georg Vorlaufer agreed to give a talk today. He studied in Wien, where he did his dissertation on vacuum and surface physics, and then started off in the software business, software development business, changing a couple of times. And in the end, now he is currently already for quite some time, nearly 20 years, a scientist at the AC2T Research Center in Austria, which is very well known for tribological research. And today he will talk to us about the application of AI or machine learning methods for the analysis of tribological data sets and show us use cases and challenges. And with that, Georg, the word is yours.
Yeah, thank you. So I will share my screen, just a moment. So can you see the right screen now? Probably not. I have to share another one. So let's see this one. So just a question. Can you see my screen?
Yes.
Yeah, perfect. Yeah. So thank you, Norbert, for the kind introduction. So I will be talking about AI and ML methods in the framework of analysis of tribological data sets. And I would like to give my, let's say, talk a bit about hands-on use cases or applications, which we have carried out in the last, let's say, two and a half years here in our institute. Yeah, so I hope it will be interesting for you and you can learn something. We learned a lot, and I will give a very short, let's say, lessons learned summary in the end of my talk. Okay, so with that, I would go into the introduction, and I would like to introduce myself first. So my name is Georg Vorlaufer. I'm Austrian, and I studied in Vienna what is called at the time Technische Physik, which is basically a study of applied physics at the Technical University in Vienna. as you can see, it took me quite some years to complete my graduate studies. That's why, because I was always, let's say, inclined on working with software, and I have starting coding and software development at the age of 13. So that's why it makes it up of 40 years of experience in that field. Okay, then I did my doctoral studies at CERN in Geneva, where I worked on, as Norbert already said, on vacuum and surface physics. So I was always inclined to more to experimental aspects of physics than to theoretical ones. But at ACT Research, where I've been now working since almost 20 years, I switched my focus first to modeling and simulation. So that means I have kind of 20 years of experience in finite element modeling, for example, or mathematical modeling in general. And of course, tribology, which is our research focus in the institute. Yeah, and since about 3 years, I'm responsible for activities around data science at ACT. And with that, let's say, function or these duties, I would like to give my talk today. Okay, so short facts about ACT Research. As most of you might know or might not know, we are one of the largest private, that means non-university tribology research service provider in the world. About 140 employees, and from that about 100 scientists in the different fields, which you can see here, which highlights basically the interdisciplinarity of the research field which we are working on. And yeah, we have a quite large laboratory space and office space. We are running a publicly funding project which is called In Tribology, which I will talk about briefly later on. Our approach is basically, yeah, it is what I would call a systemic approach. So we have groups which are dealing mostly with materials, with surfaces and friction, with lubricants, and we have a huge, let's say, R&D infrastructure, which consists of tribometers on one hand, but analysis instruments like mass spectrometry, secondary electron spectrometry, and other high-end analytic equipment. And of course, quite some tradition in multiphysical modeling and simulation. So Michael also did part of his PhD work with us in ab initio modeling. So that's also one of the activities which we have in-house. And what is lately coming more and more important is about digital transformation or digitalization and the related methods of data science. So talking about our publicly funding research program, which is basically accounting for 3/4 of our total turnover, I would say, is we started with the latest research program in 2020, and it's going to end officially in about 1.5 years, but we have the chance for an extension until March 29. And within this 4 years period now, we have some target values, which are about 200 papers, 45 PhD theses, and some master theses. And our consortium is about 80 companies and 40 scientific partners. So just to give you a very short impression what our company partners are. So they are basically well-known companies in the field of production, in the field of automotive industry, in the field of material development, all over the world, but of course, mostly concentrated around Austria, I would say. And our scientific partners are also, yeah, you might recognize one or the other quite well-known institute here. Okay, so that is about a very short introduction about our institute. And now to the, let's say, motivation of why we do data science at ACT. And that motivation has been outlined in this schematic graph here, which was also basically the heart of our proposal for the current research program. and that is that the data is the core of our research, basically. So we are on one hand doing fundamental oriented research, but we would like to transfer this research to some industrial relevant solutions and to answer questions which are relevant for daily life, if you want. And to our point of view, data is the central piece here. And that is the rationale of our activities here. So we adopt methods from data science and integrate them in our, I would say, in our daily research work. And what we consider AI and ML, because that is the specific topic of this seminar series, is that we consider AI and ML as being only one part of our data science activities. And it is a very powerful tool to assist research with large data sets. But we are also aware of some problematic aspects, and I would like to highlight them also, because I think people are often not so wary about these implications. And that is, okay, AI has some current hype, I would say, which is also carried through politics and through you know, marketing aspects, and I think that raises a lot of probably false expectations also. And we have, I mean, there are discussions going on about the ethical aspects of AI and letting the computer overtake too much responsibilities, if you want. So one has to be careful about that. And one other problematic thing in my point of view is that especially deep neural networks, they are very, yeah, well, they are not deterministic in a way that a human can explain them or understand them properly in their decisions. And I think that is a dangerous point, or at least a point where we in research should care about, actually. And then at the third point, which I would like to highlight, is that AI and other data science methods, I would say, are inductive in their nature. So that means when you think about the philosophy of science as put forward by Karl Popper, for example, then this is an apparent conflict, and we should deal with that. We should be careful on how we use AI in our research. But that said, again, it's a powerful tool. It can help us to shorten, for example, very complicated computations, as we have heard already. And it is a tool to assist our research, and we should use it properly. So that said, a short overview of what we do in our data science activity at ACT is, of course, we have a huge part which is more or less the generic or classical data processing, which goes from data acquisition to storage management. And I will tell you in my lessons learned statement that this is something which is not to be neglected. And of course, all the data preparatory steps like filtering, outlier detection, visualization of data, this is a huge topic which takes resources and takes time. So that is something which for us is very important. Then of course, statistics, let's say what I would term the mathematical or the classical statistics is a very powerful tool as well, and a lot of modern developments go on here into, for example, robust statistics or regression methods, which are very advanced. Also the topic of designing experiments, the topic of clustering and exploratory statistics like principal components analysis. That is something which can help us to deal with this data which we have. And I will give you an example about that later. And then, of course, the actual topic of machine learning in AI is also part of our research or our activities. And here we have adopted methods from supervised learning and unsupervised learning. And I will also give you an example about that. Okay, so that's about my introduction to the topic from my side. And now I would like to switch to the application examples as promised. So I put together 3 use cases or 3 application examples which deal with all the 3 aspects of data science which I have mentioned before. These are all published results, so I will give you the references to the relevant papers at the end of each of these three sections. And we start by looking at what I would say is the foundation of data in tribology, and that is Tribometer Experiments, and here specifically about the pitfalls or the intricacies of doing tribometer tests, and that is the dynamics of the machines themselves. So if you look at a typical, this is really a prototypical tribometer, is a pin-on-disc tribometer which has a rotating disc, and a pin which is pressed by a loading mechanism against this rotating disc. And then you have typically a force measurement which is measuring the normal force and the friction force using, for example, a cantilever or other system. You often also have some kind of displacement measuring device which would give you an indication about the total wear which you have already produced. But and this is a mechanically seemingly very simple machine, yeah, but it is not as simple as it might seem, because the disk is never completely flat, and it is probably not even possible to mount it in such a way that it's completely, let's say, the surface is normal to the rotation axis. Yeah, so it has a certain tilt and it has a certain waviness. And if this disk spins fast enough, it will give rise to some dynamic excitation of the system. And if you are unlucky, you will run into one of the eigenmodes or the eigenfrequencies of this system, and it will behave in a way which will basically shadow your actual measurement data. So it means that the friction force and the normal force, for example, is actually what you measure is a contribution of the actual contact forces you have, but then to some extent also the dynamic forces in the system. And if you analyze these kind of signals carefully, you can actually separate some periodic features from the actual, let's say, signal which you want to detect. And if you do that, you can actually reduce what is an apparent noise in the signal. So here again, the schematic view. So we have a pin on the disk. We have some sponge which applies a certain defined amount of lubricant film on the disk, and we have a sensor which indicates the zero position so that we can detect the number of rotations of this disk. The core thing here is that you have to acquire the data at enough high sampling rates to resolve, let's say, the individual cycles. So that means if you have, for example, a 50 Hertz or 3000 RPM rotations, then you need at least, let's say, 5 kilohertz sampling rate to resolve in a reasonable way the individual rotations. And when you do that, you can group and split the data on a cycle basis, and you can employ different data analysis techniques to visualize or to analyze what is happening dynamically in this tribometer. So here, for example, what we have here is on the left side of this slide, you see what is called a periodogram, or a output of a time frequency analysis, which reveals, on one hand, the parallel lines which you see here are basically the harmonics of the rotation of the disk itself, and then the vertical lines would actually show you different regimes of operating conditions. Yeah, if you have a lot of noise, that means the system is running unstable. Then you would see basically frequencies appearing or amplitudes appearing at each frequency. And if the system is running stable and clean, you will basically only see the harmonics. So this is a very important visual tool to help to understand what is going on in the experiment. On the other hand, what you can see is that you can basically, on a cycle resolved or time resolved basis, you can see how the system evolves over time. So tribology or tribological testing is always combined with some certain run-in period where the two surfaces have to adapt to each other, and then to go to some state where the system behaves stable, and normally this is accompanied by a change in the friction force, for example. So this is all classical conventional data analysis, I would say, and it is very, very powerful to understand what's going on in the experiment and to help you to get clean data. Another important aspect is that you should actually evaluate the data which you get on a cycle-based analysis. That means take one cycle after the other, look what are the periodic features and what are the non-periodic features, and then you can actually reduce the error bars or the uncertainty of your data in a great amount. And this, of course, will give you, for any later data analysis step, which will give you much more reliable and clean data, I would say. So that's what you can see on the right graph here. We have an example. We repeated the same experiment 10 times. We see that we get quite reproducible, let's say, values for the coefficient of friction. And if you would basically, what is sketched in the left graph, if you would understand that the blue data, the raw data, are actually comprised of a cycle average and a periodic signal, then if you remove the periodic signal, then the noise gets reduced dramatically. Another very powerful tool which we developed in our company is what we call a 3D visualization of cycle data. And here, basically, what you can see is that you on one axis you plot the in-cycle position. In our case, it's simply the rotation angle of the disk, but it may also be in a linear oscillating test rig. It may be the position within one cycle. And on the other axis, you plot the cycle number. And then you can clearly visually see and also measure, of course, effects which are localized. That means which happen only in a certain position of the disk in this case, and which are transient in nature, which happens everywhere. And this is, to my point of view, very useful in any kind of tribometrical experiment to get a clear idea of what's going on in this experiment, and then, of course, to pre-process your data for further analysis in a good way. Yeah. So as promised, I give you the reference for this work. So it was published in Friction in 21, and it's open access. All right, so then let's continue with the next example. And this is now really about machine learning itself. So again, I would like to start with some motivating statement. So what we have here is basically a laboratory setup in a linear oscillating tribometer, where we test a self-lubricating journal bearing, which I will show you later a picture of how that looks like, in an oscillating motion against the shaft, the steel shaft. And the idea is to mimic in this experiment the real-world behavior of this machine element. Here are highlighted some of the, let's say, the operating conditions. And what we have done is we have equipped this machine with force sensors, with thermocouples, and with a microphone to get data for algorithms which would actually detect states of operation later on. Yeah? So these experiments are here carried out by setting a certain threshold on the maximum force which we can transmit, and when this force is reached, it is stopped, and this is typically after 50,000 cycles, and we have 9 experiments. And that is what the typical output of such an experiment is prior to any classification or machine learning. So that means we get this time series data of for example, the coefficient of friction, of the temperature, and also the normal force or contact pressure in this case. And then one of our experts or a team of experts would actually go and start interpreting these results, and they would give annotations to that. So they would write here, for example, here's a critical piece of operation. Here's something happens with wear debris sticking in the contact. Here we have a zone of steady operation, and here we have a terminal failure. So that is typically how data could be labeled actually by an expert. And now the goal for machine learning is, what if we could train an algorithm which detects this kind of states, let's say automatically, and identify at least critical operating regimes early enough so that we can either, let's say, take countermeasures, for example, to add some lubricant, or if we could then stop the experiments at an early stage to actually investigate the root cause of such a failure. Yeah, what you can see on the right side of the picture are some let's say photographic images of the damages which we observe in this bushing or in this bearing, and these are typically scratch marks or wear debris sticking out somewhere, and this will actually lead to terminal failures, which are sometimes described as scuffing or yeah. And we would like to be able to stop the experiment at a time when this starts to happen, so that we can take out the samples from the experiment, and we could then put them under a microscope or put them into a scanning electron microscope or do whatever, not to analyze what is actually going to happen here. Yeah, what we would like to do is to classify the state of the operation based on sensors which are already available on the machine. And what we would like to do is to let the expert actually give his input or her input on the classification scheme. That means provide labels to the data set. Yeah, these are the typical steps to go. I would not go into the details here, but just jump into the data labeling procedure. So what we had, as I told you, we had 9 experiments, each consisting about 50,000 cycles. So the goal was to label each individual cycle of each experiment. Of course, that is very tedious to do if you don't have any help for that. And we employed a procedure where we exploratively examine the data using PCA and k-means clustering to give us some pre-knowledge about what labels could there be, and then we let the expert adjust basically the labels based on his experience or her experience, and end up with a labeled data set which is shown on the right side of this picture. Okay, and then we tried 3 different approaches to actually classify this data. The first approach, okay, I forgot to tell you, okay, how did the manual labeling go? We actually plotted the shape of the friction data over each other and checked where are, at least from the visual inspection, where we can see differences, and then we would basically adjust the labels which were done pre-given by the k-means clustering algorithm. So yeah, so the first effort we made was using a random forest algorithm to train the data, to classify the experiments according to these 5 labels which we have given, or the 5 classes which we have given before. This is just a very short sketch of how we do that. I mean, I think for all of you who did some machine learning, the procedure is probably the same everywhere. So you take a test data set from 4 experiments, you split it into you take a training data set. So you split it into a training set and a test set, and you train a random forest classifier. You make a cross validation against the test set and get some trained model for that from that. And the details are of course hidden more or less in the routines which we take. In this case, we take the scikit-learn library for Python to do that. And then to test or to check if the quality of the classification is satisfactory, we apply the trained algorithm to unseen data. That means we have, from our 9 experiments, we've taken 4 to train the algorithm, and then we take another one from these 9 experiments to test the quality of the classification. And here what you can see, this is a typical outcome of such a test. It's called a confusion matrix, where you actually plot or have a graphical representation of the prediction accuracy, if you want, of this classifier. And yeah, as you can see, the classification of the majority of the states is very good. So that means the steady state 1 and 2, which is the one which occurs most frequently in our experiments, are recognized very well or classified very well. And the other states, pre-critical and critical, are also, so that let's say the prediction accuracy is above 80% in all cases, which is, for this system, I would say, quite a good score. Sorry. Okay, so to go on, as a next step, we took the microphone data and we tried a bit a different approach using what is called a variational autoencoder, which is actually a neural network, to try to detect at least 2 states, like which are called here normal and abnormal. So the normal states would correspond to what was called steady 1 and steady 2 before, and the abnormal state was all the rest. And we tried to use the microphone signatures to train an algorithm to predict when an abnormal behavior is happening. This was actually done in cooperation with our scientific partners from Switzerland, from the EMPA in Thun, and they developed the algorithm together with us. So let's say that the anomaly detection with a variational autoencoder will work after the following scheme. You have a variational autoencoder which consists of a layered network here, convolutional neural network, and you take, or we took, data from the normal regime signals, split it into 70% of training data, 20% of calculating a threshold, which would say then later on if the state is still normal or not. And then we took 10% for testing and mixed them together with signals from the abnormal regime to see if the algorithm can really discern between, let's say, normal and abnormal regime. And the outcome is that the accuracy for prediction is 97% for the normal regime and about 80% for the abnormal regime. And yeah, this was, to our opinion, a quite good accuracy. Yeah. And the third, this was the last effort on this data set, which we did, is we go back again to the force data and we tried to check if we can achieve similar things with the force data, which are probably not as significant as acoustic data, but still much more readily available and more easy to process. So in this case, one of the students which we had was trying out a long short-term memory-based encoder-decoder network, which is again a deep neural network to learn the early onset of change in behavior. So the goal was here actually how much before actually the anomaly starts, we could actually detect a change in the signal. Again, we split the data into training and test data sets. That's always basically the same procedure. And what we could actually see here is that about 5,000 cycles before the force signal would actually indicate abnormal behavior, this algorithm could already predict by a largely increased reconstruction error that something is going to happen. And this, of course, is to my opinion, the right way or the right tool if we would like to actually start investigating our system before it is damaged too much. So again, we have 3 papers on that topic corresponding to these 3 steps which I just told you. So the first one is about the random forest classifier. The second one is about the microphone and the variational autoencoder. And the third one is about the long short-term memory encoder decoder. And these are all public, I mean, open access. So you can access them if you want. Okay, and now since I'm running out of time, I go to the third example, which I have prepared. And this now deals with engine oils. And the methods here are more on the classical statistical side. So again, starting with a motivation, what our colleagues from our chemistry or lubrication group observed in a long years of collecting data in field tests in passenger cars from engine oils is that about 1/3 before the envisaged oil change interval, the modifiers which are in the engine oil, which would actually reduce friction and prevent wear, they start to degrade or they start to disappear, if you want. And one of the most prominent additive in such a engine oil is what is called ZDDP. And this is an anti-wear additive which degrades by oxidation or partial oxidation and then loses its ability to prevent wear. And you see that in the chemical composition, which we use here to identify the state of the oil. I will come to that in a moment. But you also see it when you take this oil and do some laboratory friction and wear tests, you see that the friction force or the coefficient of friction and also the wear rate will increase when the oil is almost basically at the end of its life. And yeah, here are just some example data from our friction and wear tests in-house. So you can see that the coefficient of friction rises and also the wear volume or wear rate rises. And here you have also plotted the let's say the concentration of ZDDP in the oil, and of course, in contrary, the iron content in the engine oil will rise because of increased wear. And this is the observation on a qualitative level, and the motivation, of course, is then to actually devise some statistics or some procedure where you can model this data and give some more quantitative correlations between the different aging states of the oil. And one specialty which we have in-house is that we have put up some laboratory equipment where we could simulate this oil degradation under well-controlled laboratory conditions, what we call artificial alteration. And the question is, of course, always, are these artificial aged oils comparable to the natural degraded ones? That means which actually were destroyed in the car engine. And so that we have here a cooperation with Professor Filzmoser at the TU Wien, who is a well-known statistics expert. And with one of our joint PhD students, we are dealing with this topic here. Yeah, so we have oil samples from a passenger car, which were collected in a let's say in an operating range of about 20,000 kilometers. And then we have two different artificial aging setups. One is called small scale, which is just a laboratory device of this big, where you can probably age 1 liter of oil. And then we have a large scale reactor, which can operate a barrel of oil. Yeah, the chemical information is obtained in this case using a Fourier transform infrared spectroscopy, which actually measures absorption bands. And chemists, this is a very well-known procedure for chemistry, for lubricant chemistry, and the experts in the chemistry department, they can actually assign certain, let's say, products of the lubricant to certain bands in this spectrum. And this information should be used to devise some, let's say, quantitative correlation techniques. Yeah, so the first effort was to use more the exploratory, let's say, aspect of statistics, namely the principal component analysis, to check where the biggest variation in the spectra might be. And what we have seen here, this is a master thesis of one of our colleagues, that basically the first principal component, which explains something like 96% of the total variance, is very well correlated with the oxidation state of the oil. And when you compare that with an oil from a different reaction process, that also is true for this other oil, but the second principal component will show quite significant differences. And what we can do is we can project the data from one aging process to the PCA space of the other aging process, and then you get a very clear view on what is different between the two processes. And okay, I'm not a chemist, so for me this spectra would mean nothing, but a chemistry expert can tell you immediately what these two peaks, which are shown here on the black graph, what these two peaks would mean in terms of chemistry. So this is basically a tool to help experts to analyze their data, I would say. What we also did is we did employ partial least squares regression method to correlate our chemistry information with the wear and friction information which we got from the tribometers. And basically, again, the interpretation is up to the expert what that means, but the correlation is not so bad, I would say. And finally, we employed, let's say, more modern statistics methods like lasso regression to actually correlate the mileage in the field to some duration in our reactor in the laboratory. Again, as promised, here again the publications. I think this one is not open access, but all of you who probably have university access might download it. The master thesis of our colleague, and finally the latest paper about the lasso regression, which is published in Chemometrics and Intelligent Laboratory Systems, and this one is open access. Okay, so I will finally come to a summary and some conclusions. The summary, I would like to say that we have a few application examples here which demonstrates the various aspects of data science in our research, and AI and ML is only one of them. All examples are real data, so real data from experiments. And we always have the domain expert knowledge as an important input in our examples. The findings which we publish or which are reported here are limited to the specific system at hand, and we make no claims about transferability to other systems. Finally, yeah, our data science activities are motivated by practical research questions, as you have seen, and we do not pursue data science as an end in itself. We are users of data science, but we have good partners which are really experts in the field, and they help us to keep or to go beyond the state of the art in the methods which we use. Okay, and finally, some lessons learned as promised. Okay, methods and algorithms, as most of you know, we have huge sets of publicly available libraries like scikit-learn, like PyTorch or TensorFlow, which can help you to actually go about with AI, for example. They are not so hard to adopt, actually. But the biggest issue is the availability of data. And that means you have to invest time and money to produce enough data to actually do big data in tribology. And you must also thoroughly prepare this data. So that means that is a time effort, a cost effort, which you should not underestimate. And to our experience, it is always best to use as much domain expertise as you can get hold of. And yeah, if you would like to plan ML activities on experimental data, then please check out the amount and quality of data and choose a learning strategy which is suitable for that. And also calculate, I mean, in terms of time and money, how the effort to generate this data. I would estimate that is about 90% of the total work on data science is about preparing the data. Yeah, and of course, try to get a ground truth and validate the outcome of your AI algorithm or machine learning algorithm. Okay, that's it. I have to acknowledge our research program, which is funded by the Austrian government and also by the province of Lower Austria and Vorarlberg. And yeah, an invitation in the end. We are open for cooperations, and if you're interested, please don't hesitate to contact us. Here are our coordinates. So just give us a call or write us an email. And that's the end of my talk. Thank you.
Thank you very much, Georg, for this very, very, very interesting talk and the lot of things that you showed there. So now for question time, I don't see any questions in the chat yet, but I do have one or two questions actually. So the one question is kind of linked to your last slide, and it's kind of two questions. So the one question is, how much data do we need? So if I am coming from the field where I am more in, so it's rolling element bearings, so then we already know for lifetime we do a lot of experiments to get statistical data, but they cost a lot of money, they run long time. So we say, okay, maybe 5 experiments with 4 bearings per experiment, and we say, we can start to trust the data, but if I have to train some machine learning on this, I think this will not be enough. So how big a data set would you say is the minimum I would need to start doing this? Yeah. And then just as an add-on, do you see any chance of a lot of the historical data that is available? So be it in an institute, that experiments that have been done, or other data available publicly, can be, let's say, included in this without problems? So there's actually 2 questions.
Okay, so then I will answer the second first, because that is more, I can give you a better answer on that. So the historical data sets are fine as long as you have good metadata. And that is the that is the but here, because at least I know it from my institute or from our institute here, is that you always do experiments on a specific purpose. And you normally don't think about the more general, let's say, afterlife of this data. And that means when you come back 10 years later and you would like to address a specific question and you look at this old data, you probably miss the crucial information because it has never been recorded. And people tend to forget, and you can start searching in old reports or old publications if you find still some useful information. And that costs you an enormous effort. Yeah. So that is what we learned ourselves. And our strategy now is, when we plan experiments for any project, actually, that we try to record or to be as clean as possible in the notation or the annotation of data with metadata, and also the point of managing those data. That means, where do you store them? How do you store them? Do you actually record the storage format? Do you have the software to read them in later on? And all these aspects are actually crucial for using historical data. And to my experience, if you have not been very careful in producing that data at the time you produced them, this historical data might not be very useful. So that's probably more a matter of quality management or foresight, if you want. Yeah, so that, yeah, if you're lucky and you have an institute which has a long history of good quality metadata annotation, then you can use this data. Yeah? And the other thing concerning how much is the minimum data set necessary, I would say the more expert knowledge and the more physics you put into your learning strategy, then the less data you need. Yeah. Okay. So yeah. I cannot give you an absolute number, but I mean the recent developments, what we are also looking at is what is probably called physics-informed or hybrid modeling or physics-informed learning. Also labeled or supervised learning might be more suitable in this case if you of tribological data, or let's say data from such tests. Lifetime tests are extreme case where you have to run experiments a very long time normally, and you get only a few basically lifetime points in the end. Or you even try to use well-known classical statistics instead of machine learning, yeah, to access information about your data.
Yeah, thank you very much. Yeah.
Okay, I have to repeat what I just said because I was muted on the stream. We have a couple of questions in the chat now, and I want to first relate a question from Nick Garabedian, who gave a flash talk together with his student Ilya Bavon. I don't remember the last name of Ilya. Sorry, Ilya. But basically, I think this is very suited also to the whole topic. Maybe you should go to YouTube if you have not yet checked it out and listen to those flash talks. And he asks, "Hi Georg, that's an awesome collection of works. Where could we find the data and code associated with the papers that you presented?"
Okay, good. The data in our institute. So, yeah, I mean, we could think about sharing the data if we could find a way of collaborating, I would say. The point is that this paper were recorded with this data were recorded with an industrial partner, so we have some kind of confidentiality requirements here. But probably we can, if we can talk a bit in person, we could probably find a way of sharing that data under certain conditions, which means, for example, scientific cooperation. The code is in our institute. We have currently no intention of making it public in a way that is not because we don't like to make it public, but because the effort in documenting it correctly and making it useful for the community is not where we have currently budget for. Still, what we are using is as I said before, is standard publicly available libraries as for example, scikit-learn, PyTorch, and TensorFlow. Yeah.
Okay, then relating to that, I want to do a couple of questions by Vivimat, which I think might be Stefan Eder. So first of all, answering this question, he says there is actually an existing contract between AC2T and the Karlsruhe Institute of Technology where Nick works, so maybe you can work something out there.
Okay, perfect.
So NDA should not be a problem, so maybe you can get together.
Yes.
And then there was another question from probably Stefan. If one wanted to contribute some existing data to such an evaluation, what would be the minimum requirements with respect to self-consistence?
Yeah, I mean, the expert should actually have a educated guess on what is outliers, what is reproducibility of the data. So you should have at least a few repetitions of the same experiment. We have actually not yet established a quality measure. We are working on that, and this is a hard topic actually to actually assign a number of, let's say, a confidence level on, for example, the coefficient of friction or something like that, because we know from our past that tribometric experiments might exhibit a lot of outliers, a lot of variation in the data. Even using the same machine on different institutes, we have some kind of round-robin tests for SRV tribometer, for example, which produce a very high variation in the when you go from one institute to the other. I mean, what we would need to do probably is to train an algorithm on a mixture of experiments from different institutes to get it suitable for the data at hand. Yeah. So what we did, for example, is that we mix the data from 4 different experiments into one training set in order to make an algorithm which is more capable of predicting outcome of unseen experiments, which are hopefully within the range of the seen experiments. Yeah. So that's hard to answer. We have to define a use case where we collect data from different institutes to see what is the variability, and then to define a certain window of let's say levels of data where we can work with. So I think the biggest problem with this AI and ML algorithms is once you go out of the defined training of the domain of the defined data set, yeah. So the extrapolation quality is, I mean, I would say questionable at least, yeah. So if you go away to a different domain or outside of your domain of where you trained your algorithm, then I would highly doubt that you're, at least at the state where we are now, that an AI or an ML algorithm can actually give you useful predictions. Yeah. So we have to define the range of parameters where we work first, and then we can contribute data from different institutes easily if we are within this range. Yeah.
So maybe another small question from the chat, also from Vivimat. So are simulation results better suitable as they are more likely to have useful metadata?
Yes. How? Yeah. I mean, that's another thing which we are currently working on, and the question is how you would. I mean, I know that there are efforts, for example, in the DFT community to use AI to predict structures or energies from a few, let's say, cornerstone DFT calculations. So you are much more expert, Michael, than me on this field. So yeah, we can try it out with I mean, what would be the variability in the input of your data when you use simulations? Yeah, so you have to do some variation. For example, when I would think about FEM simulations of machine components, for example, then I would vary some tolerances in the construction, for example. Yeah, so if you have a bearing and a shaft and you would like to study the outcome of a simulation under the variation of construction tolerances or fabrication tolerances, for example, yeah, or uncertainties in the material parameters or something like that. Yeah. Otherwise, I mean, a FEM simulation is a deterministic result. You will get always one result, and why use an AI algorithm for that then afterwards? Yeah.
Yeah, that's, I think, very good. Thank you very much, Georg, for these answers. I think we don't have too many other questions. I still have some questions, but I think we can discuss them maybe in person at some point when we meet. And then I would just say we can continue onwards with our program. So let's thank Georg once more for his great talk. And then we will move on towards the...
Yeah, I will stop sharing my screen, yes. And I will say goodbye at this point and hand over to my colleague, yeah?
Yes, exactly. So that's a good handover also, because we are now starting the section of the flash talks, which works like this. We will have 3 short talks, 10 minutes in length. They will follow each other without a question session, and we will have the question session after these 3 talks. So if you have questions, write them to the chat, the YouTube chat. They will be collected, and then in the end, the discussion will be with all the 3 flash talkers. And with that, I am happy to introduce Manel Ripoll, also from I call it AC2T Research GmbH, so working at the same company as Georg, who will talk about friction control in extreme environments using laser deposited self-lubricating alloys. And with that, Manel, you can share your screen and you have the stage.
Okay, let me see if it works.
That looks good.
Okay. So thank you very much for the introduction. In this flash talk, I would like to share some snapshots of the work that we have been doing in the past years on the development of self-lubricating alloys made by laser deposition. And this work was mostly done by our colleague Hector Torres, who was at that time a PhD student, and now he is scientific staff with us. So why do we need self-lubrication in extreme environments in particular? Well, the point is that there are some applications like aerospace or high temperature forming processes where lubrication is challenging. It's not impossible, but it's very demanding. In aerospace, for example, we have vacuum, so we have outgassing of conventional lubricants. So due to the vacuum, it's complicated to have some efficient lubrication. And also at high temperatures, conventional greases and lubricants degrade very quickly at temperatures over 300 degrees. And there are other alternatives that are always coupled with disposal, safety issues, and also environmental issues. So in those 2 applications, the use of materials that are able to have some intrinsic low friction would be of a very high advantage. And why laser deposition? Well, laser deposition is one of the additive manufacturing techniques. It's called laser metal deposition. And basically by these techniques, we can produce layer by layer several samples. It doesn't have the precision of other techniques, like for example, selective laser melting, but it can produce very large and bulk materials, and it can also be used for repairing and refurbishing. So it's also a very efficient technique in this sense, because it's also cost effective. It provides, for example, when you use surface functionalization, it provides functionality only in that places where you need it, which also can be very convenient in many applications. And it also can be coupled together. It fits very well also with other additive manufacturing techniques. So like, for example, in this example here in the bottom, so let me put the pointer. So in this sample here, you can have a sample manufactured using, for example, selective laser melting, and on top of it, you can have a laser metal deposition for surface functionalization. So this is a very convenient method, very modern approach. It's a novel manufacturing approach, but it also has some challenges in the material deposition. The point is that, for example, if we have a nickel-based alloy and we want to make it self-lubricating, we need to add some solid lubricants. For example, silver is a soft metal with a good shear, with a low shear properties, but nickel and silver, they are not miscible. So if we melt them with a laser, we end up having some microstructure like this. So it's a substrate with a nickel-based coating with a huge silver bubble on top of it. So this is completely useless. So it's just a fancy way of wasting silver. So if we want to have something useful, we need to have this solid lubricant homogeneously scattered and distributed in the microstructure. And to do this, we need to have some diffusion barriers for the silver, and we can do it using, for example, sulfide compounds. So in our case, we use molybdenum disulfide that during the thermal deposition decomposes into chromium sulfide. This means that it's not limited, this process, to molybdenum disulfide. It also can be used other sulfides as a precursor, but once we use these sulfur compounds, we end up having this microstructure with the characteristic nickel, dendrites, the silver, like these light gray silver inclusions that are surrounded by these dark gray chromium sulfides. We can see here the transmission electron microscopy image with more detail. You can see here this chromium sulfide compounds, the silver inclusions. This is pure silver. This is also important that silver remains as a single phase, doesn't build any intermetallics. And in the nickel matrix, we see just very little sulfur going in the form of leftover molybdenum disulfide and also of the degradation product molybdenum tetrasulfide, which is non-lubricious. So we check this nickel self-lubricating alloy under different conditions. So the first one is, for example, reciprocating sliding model experiments against martensitic stainless steel. We always use some material as a reference. In this case, we use also martensitic stainless steel. Cladding as a reference, this is the red line. And we can see here that when we use the martensitic stainless steel, friction is very high. And when we use, for example, the nickel-based alloy, we are the green lines, we are able to have a very steady and low friction. For example, look here at 400 degrees, we can have a metal-to-metal contact at 400 degrees without any lubricant and a steady coefficient of friction of 0.2 compared to close to 0.6 for the martensitic stainless steel. So very good friction performance, and at 600 degrees still managed to get some good performance, much better than the reference alloy, but already struggles a bit. We also try close to reality tribometer that it's available at Luleå University of Technology in Sweden. In this case, we have a strip test with aluminum silicon coated ultra high strength steel at 700 degrees, and we do always single pass, replace the sheet and use a new one. You can see here the results, and you can see that when we use a reference, in this case was a nickel based material without any solid lubricant, friction is high, and also we have these break-ins into the coating in this aluminum silicon coating, which spikes of friction close to 1. And when we use the self-lubricating one, in this case the blue line, we have a much lower friction, around 0.3 for every sheet, and when we change the sheet, we also don't have this break-in friction. We also get a change into the lubrication mechanism, into the wear mechanism, sorry, and we switch from adhesive wear, which is very detrimental in forming processes, to mild abrasion. Another example, also in this case, model experiments, reciprocating sliding against aluminum alloy. In this case, aluminum, forming of aluminum is very demanding, so we added some solid lubricant and check what happens when we have a lubricant starvation. And you can see, for example, a tool steel starts here with very low friction, but as soon as the solid lubricant fails, friction skyrockets and goes over 2, and we need to stop the experiment due to extremely high friction. And with the nickel base, the blue line, we see that initially friction is low due to the solid lubricant, then you end up building a tribofilm, and at some point friction gets very stable with a value of 0.5 and could continue during a much longer period. And also in this case, we see that we switch from adhesive wear to mild abrasion. But where these nickel-based materials really shine is in vacuum. So in vacuum, we tested against 440C, martensitic stainless steel. This is the reference material for vacuum experiments. And this is a pin on disc, but don't be confused because it's not unidirectional. It's reciprocating sliding, so we are moving around an arc of circumference with a constant normal load and at 2 different temperatures, room temperature and 300 degrees, without any solid lubricant, without lubricant at all. So completely dry contact. And what we can observe here, so the reference nickel alloy in room temperature or at 300 degrees has a really high coefficient of friction, very unsteady with these spikes that are characteristic of metal-to-metal adhesion. And when we have the nickel-based self-lubricating material, we see that friction is very low, around 0.25 at room temperature and slightly below 0.2 at 300 degrees. So again, this is metal-to-metal contact in vacuum at 300 degrees without any lubricant at all. And in this case, what we can observe also is that not only the friction is much better, but also the wear is much better. In this case, we have, for the reference, nickel-based cladding, severe plastic deformation, we have an irregular wear track, and we have the self-lubricating nickel cladding. Friction is very, very small, very homogeneous wear scar, and very, very narrow, very thin. And we can see here in the scanning electron microscopy image how this smearing of silver that is supported here by thermal softening at 300 degrees helps and aids in controlling friction at these temperatures. And now I would like to leave the last 2 slides with a bit of outlook. So what are we doing right now? And we thought, okay, have a nickel self-lubricating material is cool, but actually it would be much cooler to have the self-lubricating titanium alloy. So titanium is a superb material, excellent strength to weight ratio, very good corrosion resistant, but have really miserable tribological properties. And the idea is, would it be possible to have a titanium alloy with some self-lubricating properties? And we end up with this microstructure here. So this is a titanium 6 alloy, titanium 6-4, titanium grade 5 alloy. And basically these light inclusions here, this is the solid lubrication phase, which is the titanium nickel rich phase. And when we use this under reciprocating sliding at high temperature in a self-mating titanium contact, so very detrimental contact conditions, we see that friction, particularly in the range to 400 to 800 degrees, is far better when compared to the self-mating titanium contact. Even at 800 degrees, we need to stop the experiment here. In this one with a very high friction, but still continues running. And the best conditions for this self-lubricating titanium alloy is at 600 degrees, where we get a coefficient of friction relatively good and low at around 0.5. Again, self-mating titanium alloy without any lubricant at all. And finally, we came to our colleagues from Tallinn. They are working in this powder metallurgy, developing titanium borate composite materials, and we apply also this nickel bismuth addition, and we ended up having this titanium borate titanium phase surrounded by bismuth, and this bismuth phase is surrounded by nickel. And we repeated these experiments, also very detrimental conditions, self-mating titanium contact, and we see that in this case, especially at the lower temperatures, room temperature and 400 degrees, friction in a titanium self-made contact can be as low and steady as 0.4. And not only friction gets better, but also compared to the self-mating titanium contact, the wear becomes also much better. So with this, I would like to conclude. So I have shown you our initial self-lubricating nickel alloy that works by encapsulating metal sulfides on silver pockets, that it provides very good friction control in air until 600 degrees and 300 degrees in vacuum, friction reduction in different forming processes, and now our current work on self-lubricating titanium alloys. So with this, I would like to thank the Austrian COMET program for financial support, and also thank you very much for your attention.
Thank you very much for that interesting topic, Manel. And then, yes, we will move directly on to the next presenter, who is Andrea Silva from SISSA International School for Advanced Studies in Trieste, Italy. We'll talk about design principles for crystalline interfaces, directional locking, directional superlubricity, and structural lubricity. And with that, the screen is yours.
Thank you for the kind introduction and allow me to present our work. You can all hear me, I assume, and see the right screen.
That is correct.
Perfect. Okay, so yes, I'm Andrea Silva working in SISSA, and I will now bring you a bit down to a smaller scale, dealing with nanoscale friction and a bit more theoretical as well, as we are computational people in Trieste. So the realm we are dealing with is that of nanomechanical devices, so a strive of engineering to miniaturize our technology, let's say. And in this world, there are normal processes that become very intriguing, like nanoscale peeling and bending work very differently than what we are used to in the macro scale world. And especially nanoscale sliding is completely different than what we are used to. And in particular, it presents itself usually in the form of stick slip or structural lubricity, so contact with high friction and violent events, or contacts where the two things can slide freely against each other. And these are characteristics that are important to know, because like if we are building a machine on the nanoscale, we want to be sure that it actually stays in the place we put it, or it can move freely as we want it to. And these two behavior are linked by something is called the Aubry transition that can also mix one with the other. And all this nanoscale sliding is sort of controlled by the moire pattern that develops at this crystal-crystal interface. And the zoology and the variety of these patterns and specific crystal interface is very big, as we saw in the talks on Monday. So it can be probed by high throughput density functional studies, and where you can compute the potential energy surface of two crystalline interfaces sliding. And it has also been probed in the experiments where, for example, here in the case of gold ion sliding, molybdenum disulfide ion sliding on gold, the system is pushed always in the same direction, but it goes along preferential direction due to the crystal symmetry. So there is some directional locking of the motion. And at this small scale, it's also very important the effect of finite size, as it was shown in 2013 by Ditzel. When you study the friction as a function of size, you see that the friction scales according to specific rules, and in particular, structural lubricity, where the friction disappears in an infinite contact, is shown to display this sublinear scaling with the number of atoms. So the realm of the sliding friction and nanoscale, it's complex, and even to explore it, we need some guidance. And that's what we tried to do recently, trying to define a degree of commensuration and trying to answer the question of, given an arbitrary interface, by which I mean two mutually rotated lattices, what is the qualitative friction behavior to expect? So not going quantitative, like it's a step before high throughput, let's say, but like in general understanding what would be the friction to be expected by this contact. So we work on a geometrical level to be general and fast. And now I will try to summarize a lot of math, let's say, in a visual way. But first, let's build a system. So we have our system is built from a substrate potential, which has a general form and is periodic with whatever periodicity we want it to be. And there is a reciprocal space associated to it. So the Fourier transform of the real space. So we put above the substrate our adsorbate, building our crystalline interface. And this would be a second lattice with a different periodicity that can be rotated at an angle and is associated with an adsorbate. reciprocal lattice as well. So the red point here. The frictional quality of the contact, at this nanoscale contact, at least in this theoretical extended word for now, is given by the appearance of a coincidence lattice vector, which is when the two lattices match, and so that they can interlock nicely and give rise to high friction or structural lubricity. So these coincident lattice vectors are related to the moire I was saying before, that gives the quality of the thing, and we can reduce these lattices to understand the moire symmetry of the contact. And by translating the adsorbate lattice over the substrate, we can compute the translational energy landscape of such a crystal interface. So in this case, we will have directional locking, so the system will move along the preferential direction of the substrate. And just to get a bit more detail, this can be computed numerically, which is usually done in codes by really summing over the atoms building up the interface, or we did it by using a Fourier transform of the potential, which is an exact match in this periodic infinite system. So this is the case of directional locking, where friction is high and you expect stick slip. On the other hand, we would have structural lubricity, where the system can slide freely in any direction. So the energy landscape that we see here is flat. This means that the two lattices are incommensurate, but there could still be, mathematically, there could still be coincidence lattice vector in real space, but if there are none in the reciprocal one, then you would expect to see this sort of flat energy landscape. And in this categorization, we discover intermediate novel type of interface, which we call the directional superlubricity, because for specific lattice symmetries, you would have only one coincidence lattice vector, and the moire pattern would be form of dense line spaced over discrete spacing, which results in this energy landscape, which is made of valleys and ridges, where the friction is exactly zero along this valley, but retains a finite value on the, perpendicular to it. And just to go a bit back to the real world, let's say, the first case would be the one of graphene sliding on graphene, where you translate the upper layer, you go through different configuration, and you have like minima and maxima alternating. Or to give an example with the same symmetry would be nickel on nickel. The case of structural lubricity would be, for example, molybdenum disulfide sliding on graphene or HPM, because they have a large incommensuration. And we are not aware of anyone reporting a theoretical study on this directional superlubricity with this specific friction anisotropy and the scaling law I'm about to show you. As I said, like scaling law is kind of what defines structural lubricity, going from finite size, increasing the size, and the sublinear scaling. And we can describe that with this approach. So if we take a finite flake of size n, we can write the potential energy surface in real space by summing over the particles, or using the reciprocal lattice depicted down here. So we can expand in the Fourier components. And this is for a finite size flake that will go back to the one I showed you before for an infinite system. So here there are a bit of formula, but they can be broken down a bit. So the important bit is like here we have an arbitrary form of potential, just needs to be periodic, and we can write equivalently the system with in the Fourier space. The spatial distribution is given by these plane wave terms here. And at finite size, we have this weight. So all the Fourier components, which means any possible modulation of the corrugation, enter the system, but they are weighted by the specific shape and size of the flake. And in the infinite limit, this needs to give back the categorization I explained before, because this weight will just select the relevant Fourier component, which here are these matching vectors defining the moire pattern of the system. At finite size, or other components can contribute as well. So we have superposition of different modulation. So for example, we can check what happens to these other two substrate lattice vectors, so these other modulations. And we can describe analytically how these decay towards the infinite limit. So like we have like a constant term here, which is the coincidence lattice vector, and a decay term, which won't be seen at infinite size, but still very much affects the behavior at finite size. This is all a bit like confusing, I imagine, but I think it's very well visualized. So if we take a small flake and we drag it around the substrate, like here, we see that like the energy landscape is very complex, and there are many different periodicity and modulations on it. As the size increases and the system realizes its true incommensuration and the other Fourier component decay, we move towards the infinite limit of the interface. We can play the same game with the new directional superlubricity we discovered. And by increasing the size, we go from a clearly directional lock with like jumping between the minima of the potential, which are the black spots. This starts to develop friction anisotropy, and in the end, we have this true and valley energy landscape. Now we can go back to a bit more friction and measure the friction along the two directions. So if we go parallel to the valley or perpendicular to them. And what we find is that the friction scales very differently. So we have a finite friction per particle, so it's constant, perpendicular to the valleys, while along the corridor, as the size increase, these scales sublinearly. And we tested numerically how this goes for different shapes, and we see that it nicely stays between the theoretical boundary, which has these two lines. So we're still very much in a theoretical world. I just wanted to give a couple of examples where we saw this in a more real system. Not quite a nanoscale interface, but what we call a nanofriction emulator, which is a colloidal system that emulates a real atomic interface, where we have these colloidal clusters over a pattern surface where we can tune the symmetry and strength of the substrate potential, mimicking two crystals basically meeting and pressed against each other. We can drive it like in a friction experiment using the gravity, and we can see that this cluster move along the pattern surface along specific direction here, going with some directional locking. And if we probe the system along two directions, where we create a system that should exhibit directional superlubricity, as predicted by the theoretical model, we see that the friction along the valley and perpendicular to it nicely falls in between the prediction of the theory. So we are constant when we go across the ridges, and it scales sublinearly with size as we go along the valley. So one last thing that we can do is reverse engineer this process and design an interface with an extreme friction anisotropy. So we can, in this case, we took a graphene substrate and we uniaxially strain along X of about 1.8%, which is well within experimental values. And then we place a HBN flake on top of it. And we can go and see what happens as the size of the flake increases. So the system goes from the usual hexagonal Moore pattern, and as the size grows, it develops this valley up to the infinite limit system where you have perfect valleys in between them. And then we can probe the friction sliding perpendicular to this valley or parallel to them. And we find a scaling of the friction in the two directions, which is very much in agreement with what the theory expects. So there is of course, the situation here is more complicated because we use the realistic potentials, not some approximated Gaussian. So the system is constant, as constant friction perpendicular to the valley and goes down sublinearly in the other direction. So realizing in the infinite system a very strong anisotropy and structural lubricity only along one specific direction. Using numerical simulation, we can also probe the effect of elasticity, which of course affects the whole system, but this behavior is still retained. There is too much in between. And finally, you can predict also when elasticity will win over this, which for this case, it should be about 0.5 millimeter in linear size according to the critical length estimated by Sharp in 2016. And with this, I just want to thank all the collaborators and any question we'll take after. Thank you.
Yes, superb. Thank you very much for that very nice presentation, Andrea. And then we will move on directly to the third and last flash talk of the day. Ming Jun Lee of the University of Illinois will present surface structure modulation of agarose-poly acrylamide-co acrylic acid double. And with that, the screen is already visible. The floor is yours.
Hello, testing.
Yep.
Everything good?
Hear you. Yep.
Okay. Hello, everyone. My name is Ming Jun, and today I'll be talking about how we can control the surface adhesion and friction of double network hydrogels. In particular, my system will be the agarose and polyacrylamide-co acrylic acid hydrogel system. So firstly, I'd like to try and convince you why hydrogel lubrication is important to us, and then I'll move on to talk about what double network hydrogels actually are, and as well as highlight one advantage of these double network hydrogels. Then I'll move on to what I believe are the core topics for this presentation on tribology, the adhesion and friction control of hydrogels. Osteoarthritis is a common disease around the world where the lubricating layer between our knee joints have been depleted, and the abrasion of these bones result in pain and inability for the patients to walk. If this continues for the long term, it will eject little bone particles called bone spurs, and if these bone spurs circulate around in the knee joint, it will just result in further and more serious osteoarthritis cases. So this is a vicious cycle that keeps getting worse and worse. In addition, the CDC has also projected that this particular disease, arthritis, will only continue to increase as time passes. So this is both a current as well as a growing problem moving ahead into the future. To address this, hydrogels have been proposed as synthetic replacements for cartilage in our knee joint. And I believe there are two important qualities in order for a successful replacement. The first is that the hydrogel must be mechanically strong enough to withstand the compressive stress from our body weight, as well as having a low friction so that you can lubricate the knee bones during joint movement. And that's where double network hydrogels come in. Double network hydrogels are comprised of two polymer networks that are formed sequentially, so one before the other, and they commonly have different cross-linking mechanisms between the first and second network. My particular system comprises agarose as the first network, and then a copolymer between acrylamide and acrylic acid as the second network. As you can see, agarose has a physical interaction. It gelates through hydrogen bonding, whereas for the copolymer, it gelates through covalent bonds. So by controlling these two different interactions, I can time their sequential synthesis to make a double network hydrogel. And double network hydrogels can address one of the problems I mentioned earlier, where hydrogels need to be strong enough to sustain our body weight. Here I'm showing three different diagrams from three different papers. They are explaining the mechanisms of energy dissipation in the double network hydrogel microstructure. But what I want to highlight is that all these mechanisms have one thing in common, and that is the entanglement between first and second networks. So if we imagine like a fishing net, and the horizontal strings are the first network, whereas the vertical strings are the second network, this kind of entanglement between the two networks naturally leads to an enhancement in mechanical properties. Different models have been proposed, but they all have this one thing in common. And that's why I think this is the reason why double network hydrogels are suitable for synthetic replacements, at least in the mechanical space. Next, I would like to start talking about surface characterization, the adhesion and friction properties. And to begin, I'd like to just show you this diagram of AFM, or atomic force microscopy. The way this works is that there is a small and sharp cantilever with a very sharp tip that touches the hydrogel, and then a laser from above would shine onto this cantilever and reflect into a sensor, a photodetector. So as this cantilever travels along the hydrogel surface, the laser spot keeps moving, and that gives us our signal. In the following slides, I'll be showing you quantitative imaging, or QI images. This is a special mode from JPK that allows me to extract three data channels simultaneously: the height, stiffness, and adhesion of my hydrogel surfaces. I'd like to direct your attention to the first diagram on the top, the upper left. And we see a very unique microstructure for my double network hydrogel. It looks sort of like a grain structure, or even like bubble wrap that we have in our shipping containers. The elevated orange grains, I believe, are the copolymer component. So that's the acrylamide-co acrylic acid component, whereas the black areas that are lower in height, the valleys, I believe are the agarose network. And one reason why I believe this structure appears is that if you look in the second image in the stiffness channel, the valley regions correspond to a higher level of stiffness. And through common knowledge in hydrogel space, we know that agarose is the more brittle and more stiff network compared to the copolymer. So this is why I believe there are heterogeneities in the surface structure. The elevated sides are the copolymer, whereas the lower height is the agarose network. And now I'd like to show you, moving from left to right, I have this one same hydrogel being equilibrated in different concentrations of potassium chloride salt solution. And what I'm seeing, a trend that appears, is that when the salt solution gets more and more concentrated, the height is actually decreasing. The gel is collapsing. And I think that this is due to the osmotic pressure differences. When the concentration is changing, water diffuses out of the hydrogel, leading to a volume collapse, volume going smaller. Next, let's look at the stiffness and adhesion channels. And the stiffness and adhesion are also generally decreasing with the increase in salt concentration. And I believe that this is due to charge screening. And I'll talk more about charge screening in the next slide. Importantly, what I want to show you with this series of AFM images is that adhesion of hydrogels can actually be controlled if we tune the salt concentration that we immerse them in. Now I'd like to talk about the charge screening effects. And the first figure I'm showing is the swelling ratio against potassium chloride salt concentration. Swelling ratio is taking the weight of a wet hydrogel divided by its dry weight when all the water has been removed. So this is a measure that tells us how much the hydrogel is swollen, like in terms of volume. And we see that for the hydrogels, I have 3 different recipes, the 6,4, 7,3, and 8,2. These are just the molar ratios of the copolymer. But in general, as the salt concentration increases, swelling ratio of all these hydrogels are decreasing, but it's getting smaller. At the same time, the zeta potential, a measure of the surface charge of my hydrogels, are also getting stronger and stronger. It's more negative as the salt concentration increases. So what are we seeing here? What's happening? I believe that the carboxylic acid groups in the acrylic acid component, they are being partially screened by the mobile potassium ions in the salt solution, which decreases the apparent overall intrinsic charge of the hydrogel. So with this difference in the osmotic pressure, water would diffuse out of the hydrogel, leading to a smaller volume, and so the swelling of my hydrogels decrease. But wait, I just said that the charges are being screened by the mobile ions. So why is the zeta potential getting stronger and stronger, more negative? This doesn't make sense. And I think that what's happening here is that there are actually competing effects between these phenomenon. As the volume of the hydrogel is decreasing, what we're seeing is that the charge per unit volume, and therefore the charge per unit surface area of these hydrogels are increasing. So the charge density is increasing, and that outweighs the partial screening of the acrylic acid, leading to the stronger zeta potentials that we see here. This has implications on the interactions between the AFM tip, which is the method I'm using to measure these hydrogels, as well as the hydrogel surface. And this would especially affect the adhesion and friction data that we see in the previous and also the following slides to come. Now I'd like to move on to the friction experiments using different concentration of salt solution. And what I'm showing here is on the first row, it is the height channel of the quantitative imaging images that I showed earlier. And then from the second and third row onwards, these are friction maps. So direct visualization of the friction force on the surface of the hydrogels. First experiment I'll be showing is the applied load experiment, where I have fixed the sliding velocity of the AFM tip to 10 microns per second. And then I apply different forces, different applied loads onto the hydrogel, starting as small as 2 nanonewtons that you see in the middle row, followed by 5 nanonewtons, and then there are some intermediate values, and finally ending in 40 nanonewtons and 50 nanonewtons. For your convenience, I have summarized the friction force values into histograms here. So we have water condition on the first column, corresponding to the first row histogram, and then the salt solution condition, which is the second column of AFM images, corresponding to the second row of histograms. And what I'm seeing here is that the friction force is increasing with the applied load. This is as expected. It happens in both soft materials and hard materials. But what's interesting here is that the friction force on the hydrogels have decreased by at least 200 piconewtons just by changing to the salt solution condition. And this ties back to the the charge screening effects that I mentioned in the previous slide, because the surface of these hydrogels have acrylic acid groups, so carboxylic acid, that's COO minus, negative terminated. But then the AFM tip is made of silicon and it's terminated with the siloxyl groups, the SiO minus groups. So having both negative charges in the AFM tip as well as hydrogel surface leads to repulsion between these measurement device, and that lowers the friction force that's being measured by the AFM. Next experiment I'd like to show, I've reversed the parameters this time into the sliding velocity experiment. So now I fixed the applied load to 10 nanonewtons, but I changed the sliding velocity of the AFM tip, starting as slow as 5 microns per second, increasing to 10 microns per second. There are some of intermediate speeds, and then finally ending off with 200 microns and 500 microns per second. Once again, the same positioning of the histogram values I've summarized here. And what I'm seeing is that friction force generally increases with the velocity. And I believe this is due to just viscous dissipation to the solvent. The faster you slide, the more energy you lose to the solvent. And it's a feature of hydrodynamic lubrication. What's more interesting is that I'm seeing two friction regimes that are coming out from my friction maps. And in this arrow here, I like to highlight that you can see there are two peaks in the histograms, so two friction regimes. And I like to tie this back to the heterogeneous surface structure I showed you in the initial QI images. I had elevated grains that I believe are the copolymer, and then valleys that I believe are the agarose. So I think that the copolymer is giving me one range of friction values, and then the agarose is giving me a different range of friction values. This could have potential applications in microfluidics, where you might want channels with higher adhesion, and higher friction versus lower friction. To summarize this slide, I like to have convinced you that we can decrease friction on these hydrogels by increasing the salt concentration that we immerse them in. And as a side effect, we are also enhancing the heterogeneities of these double network hydrogels. To conclude my presentation, I want to bring across and remind you of two key components of this presentation. The first is that this particular system, agarose-poly acrylamide-co acrylic acid, has a heterogeneous surface structure with two distinct phases of properties. And secondly, the adhesion and friction of hydrogels can be adjusted. We can control them by changing the concentration of the salt solution that we immerse them in over time. With that, I've come to the end of my presentation. I'd like to acknowledge my advisor, Professor Espinosa, as well as the fellow members of the Espinosa Lab for their help, and NSF for the funding source. Thank you.
So thank you, Ming Jun, for the very nice and interesting presentation. Are there any questions from either anyone in the Zoom meeting or from the chat?
So no one in the chat so far, but Andrea, please go ahead.
I had a question for Manel, actually, for the first speaker. I was wondering if you have any chemical or characterization of really the interface to know what is if there are any phase transformation and what's the chemistry really that forms on the sliding interface of these complex alloys.
Yes, so we have done quite extensive characterization. It's not that trivial, that's the problem. So the talk was limited to 10 minutes, so I could not go into much depth. But besides, so we have here two main components as a solid lubricant for the nickel ones. One is the silver as a soft phase, as a so easy to shear phase, but also the chromium sulfides that are built here, they are also lubricious. Why they are lubricious and when they are lubricious is not really known in the literature. We are working on that right now. But in our last publication, we already noticed that it seems to depend on the stoichiometry of these chromium sulfides. So this, in particular, it seems that the chromium 3s2 and chromium 3s4 might be lubricious, whereas CRS might not be lubricious. These are at least our initial hints. So mostly the tribofilm is consisting on this mixture of sulfide compounds and soft metal. But the precise lubrication mechanism is still under investigation.
Because I would not expect silver to mix with sulfur much, but
no, silver it remains as a single phase, and that's why it performs at best under vacuum conditions. Because under vacuum condition, it does not oxidize. It does not oxidizes. It remains as a pure metal that's clear, but it does not oxidizes during the process, and that's why it can continue smearing. In air experiments at high temperatures, friction is mostly determined by the chromium sulfides.
I see. Thank you.
Okay. I also have a question which I would just pose to Ming Jun. So your talk was very interesting with the hydrogel friction, and if I understood it correctly, so you mostly go about measuring the friction with your AFM tip. So my first question would be, do you expect the scale effect? So if I would transfer it to the system knee joint, I have like a bigger surface sliding on a bigger gel pad. Would you expect some, let's say, scale effects? And the second thing would be like, are there any like theoretical models or calculation models, maybe similar to what Andrea is doing, of course, quite different materials, but for prediction of the friction in such soft, deformable, osmotic matter?
Okay, so to answer the first question regarding scale effects, one particular problem that we have when we try to measure hydrogel friction with a tip is that if you use too small of a scale, so maybe a very, very sharp tip that we can purchase, what you get is that you will actually puncture into the mesh of the polymer network. And then you get a lot of stick-slip effects, and then the friction maps turn out to have a lot of overblown pixel values. You just see white spots everywhere. So that's the small extreme. And then on the other extreme, on the larger surface area, like you mentioned, in our knee joints, our bones are definitely not in the micro scale. It's different from AFM. So when it comes to the actual applications, I believe that these hydrogels have to be transferred to a more traditional tribology measurement method, maybe those pin-on-disc methods. There have been such reports in the literature where people have tried to use hydrogel as the substrate, as well as hydrogel on the pin itself. They call that the Gemini contact, I believe, so gel on gel. And then they report single values of friction that are averaged over the entire surface of the gel. Unfortunately, I could not do and present that method because of the specific heterogeneities of my system, where I have two phases with two different friction regimes. If I were to transfer this to the traditional method where we average over the entire hydrogel, we would no longer be able to see the specific friction maps that I have shown in my presentation. So perhaps for osteoarthritis applications, we do need to evaluate the gels differently, but I believe I've also highlighted another potential avenue of these hydrogels in microfluidics, where we want specific channels where there are higher and lower friction. And regarding the second, you mentioned calculation of the friction properties.
Yeah, is there like, I mean, the calculation or like a model of somehow to, because it's
in I believe 2018 and 2020, one of my seniors in the lab, Tuba Shoaib, who has already graduated, she studied specifically the physics of friction on polyacrylamide hydrogels. And what she showed was that there is actually a U-shaped relationship of friction against the sliding velocity. So at slow sliding velocities, the adhesive components, the adhesive interactions between your gel and your measurement device, in this our case, the AFM tip, they are predominant contribution to the friction force. So as you increase the sliding velocity, the friction force actually decreases. And then you hit this minimum point. It's like a transition velocity she called V star. And that's where it switches from adhesive dominance to the film, the hydrodynamic lubricated dominance. And that's where I believe most of my data lies. As you increase the sliding speed, friction force increases again due to the viscous dissipation to the solvent. So we see this U-shaped relationship. It might apply to my hydrogel as well, because one of my components is polyacrylamide, but we have not determined that. And also the focus of this particular project is to achieve a direct visualization of friction on the hydrogels, which I believe, and to my knowledge, is a first in the hydrogel friction space.
Okay, thanks. Any other questions from the group here?
So I would have one from Andrea. And maybe I just didn't catch that part, but you talked quite in the beginning about the commensurability, and you mentioned that there might be a commensurable lattice in real space, but not commensurable in reciprocal space, and that is enough to get a superlubric sliding. And I always thought, like, okay, if you have commensurability in real space, that's it. Then you're screwed already. But can you comment on this a little bit more? Yeah.
That's what we thought as well. Yeah, that's what we thought as well. Actually, we were pretty surprised where Emanuele, one of the authors, came up with this example where you can have commensuration there, but not in reciprocal space. That is because at the end of the day, like even if you have like that single commensuration point, like the translation in reciprocal space are such that as they move, you will never find it again. It's like just having the origin, but if you translate, you will never end up in the same position, because for any direction, the two lattices drift in a different way, because the vector transform they have a different angle in reciprocal space. It's a very pathological example where you have like a specific angle between the lattices in real space, but the symmetry is such they transform differently in reciprocal. So you cannot devise a translation that will bring you back to the same point. So in the end, that's what gives you structural lubricity. It's the fact that the translation is not possible, not much what you see in real space.
Okay, thank you. So basically,
I have one question.
expect this to turn up in a real system, but if it would, then it would basically at worst give you like some static friction at the beginning if you're locked in this minimum, and then you would just continue sliding, if I understood correctly.
Yes, not even sure if you will be locked in that minimum. It is a very pathological case that you find in this, but it might happen for some very exotic materials in real world.
Okay, I see Manel has his hand up, please.
Yeah, I have one question for Ming. Just curious about the selection of this electrolyte that you use for your experiments, for your measurements. Why did you use this one and not, for example, PBS, or maybe you also tried using PBS or adding some proteins into your electrolyte? Or can you maybe comment a bit on this selection, and if you have experience with other media?
Yes. We selected this because it is a simple representation of an electrolyte solution. I think potassium chloride is very commonly used also in electrochemistry. And by choosing this particular one instead of more bio-related, bio-specific ones, like having proteins inside, I believe there are commercial solvents where they can simulate the synovial fluid. So that's the intercavity fluid between the knee joint. But I wanted to deconvolute these biological effects because in the next phase of my project, I'm actually going to try and use electric potential to control the friction of these hydrogels. And I want to target soft robotics applications. So that is why I have not moved into other solvents that are closer to the biospace, but this is a very good suggestion. And I believe given a targeted topic or application that I want to target, I might investigate the other solvents that you have suggested. So thank you.
Thank you.
Okay. Yeah, I think we have also reached the end of our time. Let's thank our speakers one more time. Thank you all for the great, very interesting presentations. Also the very nice mix of topics which actually do fit together somehow. And with that, we would suggest that we take a short coffee or do something else break of 5 minutes, and then we reconvene at 1600 Central European time for our last speaker. And yeah, see you then. And with that short break, we come to the last speaker of today's session, last invited speaker. This is Max Marian, and I'm very happy to introduce Max here. Max studied at the Friedrich Alexander University of Erlangen-Nuremberg, where he also obtained his PhD degree, working on numerical design of surface structures in lubricated tribological contexts. Then he stayed on a bit and is now professor in the Universidad Pontificia Católica de Chile. And with that, he will talk to us about predicting EHL thickness parameters by machine learning approaches, which is a topic that I find very, very interesting. And with that, Max, please.
Yeah, thank you, Norbert, for introducing me. I hope you can see my screen and hear me well. So yeah, thanks for the introduction. Hello, everyone, and thanks all for switching on into this webinar and my talk, and also special thanks to Martina, Michael, and Norbert for inviting me to speak today about elastohydrodynamic contacts and how we might predict their behavior by machine learning approaches. Yeah, but before we get into any details, let's start with the big picture. And why we would want to predict the behavior of mentioned contact types. According to Holmberg and Erimir, around 23% of the world's energy consumption originates from tribological contacts, and of about 20% of that is used to overcome friction, and 3% is used to remanufacture or replace worn parts due to wear and wear-related failures. So to get a better idea of what these 23% mean, let me express it in an energetic way. This corresponds to annual losses of 119 exajoule per year. And exa, that's the one with 19 zeros. I don't know about you, but I'm always having a hard time imagining what that actually means. But maybe this one might help out. So 1 exajoule corresponds to the energy of an asteroid and the size of the Egyptian Cheops pyramid hitting Earth with 20 kilometers per second. So we are losing this kind of energy 190 times a year, only due to friction and wear in tribal contacts. Now, for me, this sounds quite a lot, doesn't it? However, by really understanding tribotechnical systems and developing new concepts, new materials, new lubricants or surface technologies, we might substantially reduce friction and wear in various applications and vehicle and machinery and any other equipment. So, as stated, this covers manifold applications such as brakes or brake pads, clutches, the piston cylinder liner contact, thrust and internal bearings or gears, the cam follower, roller and ball bearings, or also load bearing implants. And within all these applications, we basically can break down the essential contact types or contact pairings or the geometries into parallel and conformal contacts on the one hand side, and on the other hand side on concentrated contacts, which we can distinguish in line contacts and point or elliptical contacts. The use of lubricant, of course, is an effective way, both in nature and in technology or industrial technology, to reduce friction and wear in highly stressed tribal contacts due to the partial separation or the complete separation of the contacting partners by an intermediate medium, the lubricant, which generally has a lower shear resistance. And deforming of a separating hydrodynamic fluid film depends on the gap geometry, the relative movement of the contacting surfaces, the viscosity of the lubricant, and also the adhesion conditions. And if lubricant is drawn into the contact, as exemplarily shown here for an radial hydrodynamic journal bearing, hydrodynamic pressure can build up, and it can thus lift the surfaces and separate the surfaces, and thus with sufficiently high velocity and or viscosity or lower loads, the lubricant or the fluid regime can be transitioned from boundary to mixed, and finally fluid or full film separation, which means first we have a partial separation of the contacting bodies, and with higher velocity or viscosity or lower load, we might have a full separation of the contacting bodies. And the coefficient of friction typically follows the well-known Streibeck curve that probably all of us are very familiar with. In the case of more heavily loaded contacts, where pressures can reach up to 4 gigapascal, which roughly corresponds to the load of 7 African elephants standing on the area of a human finger thumbnail, as we have, for example, in rolling bearings, there's some elastic deformation of the contacting partners that adheres to concentrated contact geometry, and this can generally be described by the Hertzen theory and the Hertzen pressure. Due to a lubricant, there's also a superimposed formation of hydrodynamic pressure. And in the area of contact inlet, compared to the Hertzen pressure distribution, we generally get an earlier pressure increase, which occurs to the lubricant compression. And in the central part of the contacting bodies, we have almost parallel film height. And there's an additional constriction in the outlet region of the contact, which is also accompanied by an additional hydrodynamic pressure peak. Typically, the elastic or the lubricant film thickness and the elastic deformation are of a similar order of magnitude for elastohydrodynamically or EHL contacts. And the elastic deformation and the fluid film formation also depend on the stress collective and acting on the contact. Basically, the resulting pressure and the fluid film distribution is determined by the geometries of the contacting bodies with radius r, for which we can calculate an equivalent radius, and the mechanical or the material behavior of the contacting bodies, namely the elastic modulus E and the Poisson's ratio nu, for which we can calculate an equivalent elastic modulus. Further, the kinematics influence the contact behavior, namely the velocities of the contacting partners, the velocities u, for which we can calculate some characteristic properties like the hydrodynamically effective velocity um and the slide to roll ratio SRR. And finally, of course, as relevant lubricant properties, we have the density rho and the viscosity eta of the fluid that determine the contact behavior. Depending on the operating conditions and the involved materials and the lubricant, different effects can dominate the contact behavior, especially elastic effects and or the piezo viscosity of the lubricant, which is the increase in viscosity under pressure. And using these kind of dimensional parameters that were suggested by Johnson, we can differentiate between an isoviscous rigid, an isoviscous elastic, piezoviscous rigid, and a piezoviscous elastic regime, as well as this kind of transition regime in between. So what I want to present in the following within this presentation, I would like to briefly introduce the conventional ways to numerically model such EHL contacts, and I will introduce two analytically solvable proximity equations. And then the main part, or the core part, will then focus on our attempt to use machine learning approaches to predict EHL film thickness, which was done in a close international cooperation with the University of Erlangen in Germany, the Universidad de Sao Paulo, and the Universidad de Chile. And finally, I will briefly summarize my talk with our short key findings. So let's start with the simulation of EHL contacts. Generally, this involves various physical domains ranging from, of course, the lubricant hydrodynamics, as we have seen, contact mechanics, i.e. the elastic deformation. Potentially, there's thermodynamics and fluid rheology involved. If we would neglect non-Newtonian and thermal effects, as well as mixed lubrication, which I won't put any focus within this presentation, we require both solution of the hydrodynamics and the elastic deformation. And if flow and structural mechanics interact with each other, this is generally referred to as fluid structure interaction. And since both solutions influence each other, we need a suitable coupling for the both domains. One way of coupling would be to perform a solution of the hydrodynamics, followed by a solution of the deformation due to the given pressure. And this is called weak coupling. If the step is only performed once, we speak of unidirectional coupling, and it's the most simple approach, and the interaction between the fluid and the structure is not sufficiently considered. Generally, in a weak coupling, therefore, the steps are usually repeated sequentially. So there's a bidirectional weak coupling until a defined convergence criterion is reached. In the strong coupling, on the other hand, we solve the two discretized differential equations in one joint algebraic systems of equations. Generally, it is possible to use the full Navier-Stokes equations to solve EHL contact problems. In this case, however, the lubricant has to be meshed in the gap height direction also, which makes normalization and mesh transformation quite difficult, and usually we have quite some instabilities there due to an over response of the elastic deformation to the surface pressure of the previous iteration step. Therefore, the hydrodynamics is most frequently represented in the form of the Reynolds differential equation. In the past, both weak and strong coupling have been used by various scientists all around the globe to solve EHL contact problems. The former, the weak coupling in the form of sequential solution, it represents both the first implemented and today still the most widely used coupling. And the first implemented or the first works that have been implemented use the so-called inverse iterative method. Here, the Reynolds equation is solved for the lubricant gap at a given pressure, and typically half-space approaches are employed to compute the elastic deformation. Secondly, there are direct iterative methods which solve the Reynolds equations for the pressure, and the multi-grid or short MG method accelerated these kind of algorithms, and also suitable and also the introduction of the multi-level multi-integration or short MLMI method, as well as some relaxation procedures allowed to calculate these kind of contacts at higher pressures. And with these approaches, we also have to mention the names of Werner and Lubrecht, who've been some pioneering work in the semi-system approaches. The weak coupling, on the other hand, or these weakly coupled solutions are contrasted by those of the so-called strong coupling, where we simultaneously solve the equations. But if we use the elastic half-space models to calculate the elastic deformation, we result or we get to a fully filled matrix in a nonlinear system of equations, and all mesh points basically are related to each other by integral equations, which then involves a lot of memory and computational effort. In the past, for example, already for simple point contacts, this has led to the fact that calculation was limited solely by the computer hardware, and this was one of the main reasons why in the past the weakly coupled solutions have dominated. But in order to obtain a sparse matrix and lower computational and memory requirements, Hapchi and co-workers proposed to replace basically the elastic deformation calculation by a finite element formulation, and also to discretize the Reynolds equation by a finite element approach. And due to the strong coupling, there's a very good convergence behavior of the solutions, which means a rather small number of iterations required to find the solutions. And further, one of the main benefits is also that it allows the use of commercial software algorithms already out there, like finite element software, that we just have to implement basically our equations and teach the software how to solve it with well-known and well-established algorithms. So still, HL equations are quite complex and computationally expensive, and in many cases sufficiently accurate and like a computationally much more efficient incorporation of EHL effects into higher level multi-body simulations or system simulations. Analytically solvable proximity equations are generally used to estimate integral fluid film parameters. So to generalize EHL contacts and the results, there were non-dimensional similarity groups introduced. Though we have to mention the names Dawson and Higginson, who defined a group of velocity, material, and load parameters, as well as a film thickness parameter. And they basically proposed curve-fitting regression equations. From now on, I will refer to them as proximity equations that relate those parameters based upon numerical simulation results. And later, Block and Mohs proved that these 4 parameters could be transferred into 3 independent parameters, thus introducing a load and a viscosity parameters in addition to the film thickness parameter. To estimate, for example, the minimum film thickness in an EHL infinite 2D line contact, Dawson and Higginson proposed an analytically solvable regression equation as a function of the material, the velocity, and the load parameters. And based upon more advanced isothermal EHL simulations, these parameters have been modified and extended by various authors to also cover 3D point contacts and also allowed the determination of the central film thickness. Basically, due to the transformability of the aforementioned non-dimensional groups, you can also use the parameters from the block and from suggested by Block and Mohs to calculate the EHL film thickness parameters. So basically, these are polynomial regression equations to estimate, for example, the minimum film thickness, independency of the load parameter, and the viscosity parameter. So in this case, generally the minimum film thickness increases with a decreasing M and with an increasing L. And this would be some kind of curves for the central film thickness, which is less influenced for a wide range of the M parameters. Generally, there have been several variants developed and published over the years, mostly to cover, for example, a wider range. When we compare, for example, the equations that have been suggested by Nijinven in comparison to Jamrag and Dawson, which have been traded in this or determined for data in this kind of or in this range. And mostly, they have been developed to cover wider ranges than the initial equations, and also to be valid, for example, in the more isoviscous and or the rigid regimes. And to describe non-dimensional groups and parameters or the film thickness equations, basically they can deliver quite reasonable agreement with many lubricants that was experimentally verified by the various authors, for example, by interferometric film thickness measurements. However, there could be some deviations under certain conditions due to fluid compressibility, thermal effects, or shear thinning, starvation, or also surface roughness. And all these aspects are not or have not been fully considered in the original numerical solutions based upon which these kind of proximity equations were derived. But these effects can also be taken into account if we employ some kind of correction factors, Cx, which are simply multiplied with the film height parameters to obtain a corrected fluid film thickness. In the original numerical solution, the density pressure relationship was modeled according to Dawson and Higginson, but the density was not considered as an input variable for the non-dimensional groups, and also not for the film thickness equations. We know that the lubricant compressibility plays no major role in the minimum film thickness formation, but the central film thickness formation can be influenced under certain conditions, and therefore we can adjust the predictions for compressible fluids from the incompressible approximations with the base density rho 0 using this kind of correction factor, whereby any model could be used to calculate the density at the respective friction pressure pH. The deduction of non-dimensional parameters in the film thickness equations was also both based on isothermal considerations. However, if we have high speeds, high velocity differences, or high slip of the rubbing surfaces, there might be some local temperature that exceeds the mass temperature of the contacting bodies, and also influence basically the viscosity of the lubricant, and thus also the film thickness. So for example, Murch and Wilson, they introduced the so-called thermal stress parameter Q, which also includes the viscosity temperature coefficient, and to determine the thermal film thickness reduction, basically, which was later extended to also cover the slight to roll ratio as RR. So here, basically, we can see the thermal correction factor versus the thermal stress parameter and dependency of the slight to roll ratio. Similar to thermal effects, Newtonian fluid behavior or shear thinning of the lubricant at high speeds and at high slip. This can also affect the minimum film thickness and the change also the profile in the contact center. Therefore, a number of authors came up with different correction factors. This, for example, an equation suggested by Baer, which also contains basically the slight to roll ratio, the Carreau exponent n, and the Weissenberg number. So basically, there are also some correction factors available. Also, in the original determination or derivation of the film thickness equations, some fully flooded conditions were assumed. So basically the pressure or the high elastodynamic pressure buildup can happen in any distance from the contact center. However, there are cases where contacts may suffer from starvation because there's high speeds, highly viscous lubricants, or simply there is not enough lubricant supply. And then basically the starting point of a hydrodynamic pressure generation is closer to the contact center, and the generated or the transportable lubricant film thickness basically smaller compared to the one for fully flooded conditions. And basically fully flooded conditions are reached when the distance between the contact inlet where we allow pressure buildup and the contact center, when it ceases to affect the film thickness. And Dawson and Higginson basically suggested taking the fully flooded staffed boundary M star and the inlet location of the contact into account to calculate some correction factors to also cover starvation effects. Yeah, and finally, it is well accepted that the surface topography in terms of any kind of stochastic deviations from the smooth surface due to manufacturing, or also intentionally produced surface features, or such as surface textures or structures, that they have a decisive impact on the film formation in actual contacts. And basically, with decreasing lubricant film thickness, the effect or the impact of the surface roughness is getting stronger on the pressure buildup and also on the film thickness development. And when we approach very low film thicknesses, there might also happen some kind of solid asperity contact, which we refer to as mixed lubrication, where basically the load is shared by an hydrodynamic pressure buildup and the solid asperity contact. And a first approach to also consider these influence of the surface topography was introduced by Chu and Cheng, based upon some statistical consideration of surface asperities in terms of microhydrodynamics and load sharing. And similar to the very well-known flow factor method from Patti and Cheng, they derived corresponding correction factors to adjust the minimum and the central film thickness depending on the orientation of the surface topography and also the ratio of the smooth lubricant gap to the quadratic mean surface roughness, so what we know as fluid film parameter. And to quantify the spatial orientation of the surface topography. They employed a so-called Picklinic factor, which can be, or which basically is a ratio of the characteristic correlation length of two mutually orthogonal measurement devices. So basically, this is a bunch of correction factors that can further adjust the predictions from the proximity equations. This is an overview of all the equations that exist for the minimum film thickness, the central film thickness in infinite 2D line contacts, as well as point contacts, or 3D elliptical contacts, that have been published over the years. And we can also see that there's quite some approaches for actually correcting these equations by factors addressing fluid compressibility, thermal effects, non-Newtonian behavior, starvation, or surface roughness. So what I've previously shown was just only a very brief excerpt from all the work that has been done in that direction. We always have to bear in mind that all the film thickness equations and also the correction factors were originally derived from different numerical data, and therefore they have different ranges or individual ranges of validity. And while a comparison with experimental data is difficult for infinite 2D line contacts, this possibility exists for point contacts and using experimental studies using interferometric film thickness measurement. And basically quite some good agreement has been reported, especially for the central film thickness, even when using lubricants with shear thinning characteristics and when you expect thermal effects, etc. And there's also quite a good agreement when we use these equations for the central film thickness outside of the stated ranges. But it's extremely important for the minimum film thickness that we only applied inside the stated ranges, in which basically was the base for building these kind of equations, because outside of these domains, the equations are greatly influenced and could not predict all equations very well. So 2 years ago, we published a review article, open access, where you can find much more detail and information on all these aspects. And in that review article, basically doing the research for that review article gave us the idea that we already hypothesized that machine learning approaches could provide an opportunity to predict the relevant EHL film thickness parameters more accurately and effectively, for example, in terms of speed and or also the flexibility of what we can predict. So, yeah, we have already heard quite a bit about machine learning within this webinar series. Basically, machine learning, shortly ML, and artificial intelligence, they're rising stars in many scientific disciplines and industries, and high hopes are being pinned upon them. And essentially, ML is part of AI and thus originally a subdomain of computer science. And AI and ML are formed by logic, probability theory, algorithms theory, and computer science. In the first step, ML involves designing computing systems for any kind of special task that can learn from training data over time and develop and refine experience-based models that predict any kind of outcomes. Thus, the system can be used to answer a question in any given field. And there are a number of different algorithms that can be used for ML, whereby the suitability of each of the algorithm approaches is strongly task dependent. Generally, we can classify these kind of machine learning algorithms into supervised, unsupervised, and reinforcement learning. For supervised learning, the algorithm basically learns a relation from any given data set or set of input and output. And during the learning, a teacher or an expert basically provides the correct input and output. And in unsupervised learning, the algorithm generates a statistical model that describes a given data set without the model being evaluated by a teacher. Basically, while the classification into these three learning types, supervised, unsupervised, and reinforcement learning, is well accepted in the scientific community, there's still no consensus which kind of algorithm should be assigned or can be assigned to which category. So what I show on this slide is only one possible allocation, but literature will display you different kind of classifications. But anyways, the intended usages of these numerical algorithms they're manifold, and there is a very broad variety of available approaches, ranging from artificial neural networks, INNs, to, for example, decision trees, support vector machines, or also rule-based learners. So basically, there's a whole variety of approaches that we can employ. And as already heard within the other talks within this very nicely organized webinar series, there are quite some machine learning approaches that also found a way into tribology, where they can help us in sorting through a complexity of patterns and also identifying trends within the multiple interacting features and the processes involved in tribological systems. As can nicely be seen in a recently published article collection and in a respective review article that we wrote on current trends and applications of machine learning in tribology, published in the journal Lubricants. There's an increasing number of published research that aims, for example, at monitoring and controlling and analyzing, designing, optimizing, or predicting driver systems in various fields of application. This can range from lubricant formulation to drive technology, to design of composite materials, to manufacturing or surface engineering. And it does not only cover like single scale phenomena, but we can find works on the nanoscale, on the macro scale, as well as micro scale. And the ML approaches so far have employed different kind of databases based upon experimental data, which is the vast majority of the works that has been done so far, which fits very nice to discussion we had during the first presentation from Georg Vorlaufer. But there's also some amount of studies that have employed numerical databases or even literature databases. Yeah, I won't go into any more details of all the exciting stuff that can be done. We have seen some very nice examples within this webinar series. But I would like to use this opportunity for some shameless promotion of a second edition of this special issue, which we entitled Recent Advances in Machine Learning and Tribology, which was just open for submission until mid of the upcoming year, and we would be more than happy to receive some submissions from you. So let's come back to the topic. Basically, our general idea of what I want to present the following was to train machine learning approaches to predict lubricant film parameters in AHL contacts as a function of standard input variables, as is also accomplished by the well-known proximity equations. And in this context, the work was based on the hypothesis that ML approaches can predict relevant AHL film parameters, such as, for example, the central film thickness or the minimum lubricant gap in 2D line and 3 circular point contacts more efficiently than sophisticated simulation models, and with higher accuracy and flexibility than the well-known proximity equations based upon the non-dimensional groups. Thereby, we addressed the following research equations. How accurate are the predictions of ML? In our case, support vector machines, Gaussian process regression, and artificial neural networks. As we can, for example, see the latter one exemplary on the left-hand side of the slide, compared to the proximity equations. The second research question: what is the influence of the training data if we use, for example, non-dimensional groups instead of the original input to train the ML approaches? The third question we wanted to answer was how do the artificial neural network architecture and the structure affect the prediction quality? The fourth question what is the influence of the size of the data training database? And the fifth one, is it possible to determine locally resolved film thickness distribution, like the film thickness as a function of the contact length instead only of 2 integral parameters? So our overall approach is illustrated on this slide. At first, we define the data we need, including the original inputs, the non-dimensional parameters, and subsequently we constructed a design of experiments based upon unletting hypercube sampling, and calculated all the trial points that we sampled by a finite element method-based EHL model, and also used proximity equations to predict the integral film parameters. Afterwards, we split the data into a training data set and used this training data to build a support vector machine, Gaussian process regression, and artificial neural network ML models. And we also split the data into test data to evaluate the prediction accuracy of our models. And for that, we use the coefficient of determination R squared. This slide shows the parameters that we write within the given boundary conditions for the 2D line contact and the 3D point contact. They were sampled using a Latin hypercube sampling and with 1,500 and 1,000 datasets respectively. And moreover, we investigated for the 2D case to what extent a reduced database with only 600, 300, and finally only 100 data points, how this affects the prediction quality. And we trained all the models first with the original input parameters that we also put into EHL simulation. And also we trained it with the non-dimensional parameters, G, U, and W, as well as the most parameters, M and L, and had a look what this does to our prediction accuracy. The database was created using an EHL simulation model based upon the finite element method, full system approach that was suggested by Hapchi and co-workers. So on the left-hand side, we can see the solver flowchart. And the right-hand side, we can see the solution domains. This is for the 2D line contact, and this is for the 3D point contact, making use of the plane symmetry. At first, the model is initialized using Hertzsprung values, and the elastic deformation is calculated for an equivalent body. Subsequently, the EHL problem is computed fully coupled, whereas the Reynolds equation is solved in a weak form on the boundary of the elastic body. And the whole model was implemented constant multiphysics, which is kind of state of the art now, so there's nothing really special about it. The results of the HML simulation might look, for example, like this. Here we see exemplary lubricant gap and pressure distribution for different, basically most parameters for different load and viscosity parameters. Whereas basically we can see that the hydrodynamic and or the elastic effects are more or less dominant depending on the parameters or the operating conditions. Further, we employed various ML regression methods, including support vector machine, Gaussian process regression, and artificial neural networks. All the data, the in and output, were normalized to values between -1 and 1. And the models were developed using training data to provide basically the best possible prediction for unknown test data. For this purpose, we split the data set into 85% of training data and 15% for testing. So in detail, we had a linear epsilon insensitive support vector machine. Basically, the support vector machine, it represents an object set by a vector within a vector space, and hyperplanes within these vector space are used to separate the data points, and kernel functions are used to transform the vector space into a higher order dimensional space, so we can basically separate the interlaced vector groups linearly. Moreover, we had a Gaussian process regression, a non-parametric probabilistic model that was which explains basically the response by latent variables from a Gaussian process and explicit base functions. And finally, we had a multi-hidden layer feed-forward backpropagation ANN, which was trained by the Levenberg-Marquardt algorithm. So basically, ANNs are inspired by natural brains and an architecture that involve a number of simple but very highly interconnected information processing elements, the so-called neurons. And transfer or propagation functions determine the neurons network input based upon output weighting, whereas the calculation of the output is achieved by activation functions, considering some kind of threshold value. And during the training of the ANM, the weightings and the thresholds are adjusted to optimize basically the overall prediction quality. And the topology of or the architecture of an ANN, like how many neurons are parallelly arranged in each layer, how many hidden layers there are in between the input and the output, etc. This needs to be tailored to the respective application of what we want to predict actually. Okay, so finally, let's check out some results. We start with the prediction from the support vector machine and the Gaussian process regression. There's a lot of going on the slide, but I will try to guide you through. So basically in the table, we can see the R square values against, this is always against the testing data. And in the graphs on the bottom, we can see the predicted value versus the calculated value. So basically, the closer R square gets to 1 and the less deviation from this 45-degree line we have, the better is the prediction accuracy by both the approaches. And we can see that values calculated with the HL simulation and the ones we predicted with the SVM and the GPR, that they quite correlated quite well, and that we reached coefficients of determinations of up to 0.99. So these coefficients of determination were partly higher than the R square values that we obtained when we employ the analytically solvable proximity equation. And when we compare both the SVM and the GPR proved to be slightly superior to the SVM. So when using non-dimensional groups like the UGW or the ML parameters, instead of the original input data for training purpose, the values were predicted with a substantially lower accuracy or even like totally insufficiently. The R square values that we had there fell well below 0.9 and almost to 0 for some cases actually. Like here, for example, we are approaching 0. And this like inferior prediction accuracy in our belief can be traced back to redundant input variables for the different output variables, because with the we can have similar dimensional parameters that can result from different original input data, and with similar dimensional parameters we can result or finally obtain different predicted film thickness or for example, different minimum or central film thickness. And we believe that these inconsistencies in the database led to problems in the training of the SVM and the GPR. On this slide, we can see some results for the neural networks, namely the coefficient of determination for the prediction of, again, the central and the minimum film thickness for the 2D line contact, and also for we have it for the 3D point contact. Again, the R square values are against testing data, and here we write the number of neurons per hidden layer, as well as the number of hidden layers. So the number of neurons per hidden layer, where we write between 10 and 20, and the number of hidden layers between 1 and 3. Therefore, we again use the original input values, and we can see that the HL film parameters were predicted with high accuracy, and we reached R square values above 0.99 by some of the ANN configurations. We can see that the number of the neurons within the in each of the hidden layer, it played a less dominant role, but the number of hidden layers that had a more decisive impact on the prediction quality. And therefore, the lowest R square values resulted in only one hidden layer, followed by 3 and finally 2 hidden layers with the highest accuracy. And regarding the number of neurons, the configurations with more than 10 neurons proved to be quite good. So since 12 neurons in 2 hidden layers gave us the best results, we kept this configuration for the following predictions. Here we can see also the predicted with calculated values for this kind of configuration. The 3D point contact featured slightly higher R-square values or better prediction accuracy against the testing data compared to the 2D line contact, which may be due to the considerably larger database for the latter, and some overfitting basically for the 2D case. Similar to SVM and GPR, training the data with only the dimensional groups instead of the original input parameters resulted in a downgraded prediction accuracy due to the inconsistency in the training database. We further varied the activation functions of the neural networks. This is still for the ANN with 12 neurons in 2 hidden layers after training with hyperbolic tangent, as in the cases before, as well as a sigmoid logistic and a linear identity activation functions. Please note that the output and propagation function were kept constant, and only the activation function was varied. And here we can see that the sigmoid and the hyperbolic tangent function both led to R-square values above or beyond 0.99, while the linear identity resulted in slightly downgraded prediction quality. And to minimize the efforts required to train or generate the database, generally it's advisable to keep the training data set as small as possible without affecting the prediction accuracy. So basically, we can see here the R-square values for the infinite 2D line contact with a varying number of input training data, and even when the original training data was reduced to 600 training data points, less than half the R-square values were at high level above 0.99, thus showing slightly R-square values, better R-square values than the 1,200 training data sets, which might imply some overfitting. And we can see that slowly for 300 and 100 data sets, the R-square values decreased. And the deterioration of the prediction quality can also be seen here in the graphs of the predicted versus the calculated value. Here we have the training data set with us. We're training with 600 training data sets with the training with 100 data sets. One last aspect I would like to show you is the prediction of the local lubricant film distribution. This is for an infinite 2D line contact. Basically, we use the local film thickness, in other words, the film thickness as well as the contact length parameter X as a training data. And thereby we reached R-square values of 1 against the testing data, including all the data sets and positions along the contact length that we obtained. And we can also see from this graph the quite nice prediction accuracy of the FEM-based EHL simulation model and the ANN prediction, and only in the range of the contact outlet, basically we got some kind of small overshooting here directly in front of the local constriction of the film cap. To compare the execution time of the FEM-based simulation and the ANN for solving the film thickness equations, basically, we compared it for a data set that was not included in the training data, and we calculated with both methods on the same computer with the same discretization. And thereby the ANN was basically 50 times faster than the FEM model, while the calculation time is probably comparable to what we have when we solve proximity equations. And therefore, we believe by incorporating the ANN into multi-body dynamic simulations or system simulations, we can improve the accuracy in friction and dynamics analysis or identification of critical operating conditions without negatively affecting basically the computational time. So this brings me almost to the end of my talk. I'll just wrap things up really quickly. Basically, I've shown you that ML approaches could predict film thickness parameters more efficiently than sophisticated EHL simulations. And we could verify that the ML outperforms analytically proximity equations based upon non-dimensional groups. Secondly, in contrast to proximity equation, it's important to use the original input parameters instead of the non-dimensional groups. Third, the architecture of ANNs, and especially the number of hidden layers, influences the accuracy. And for the data set of this contribution, we found that ANNs with 12 neurons and 2 hidden layers were quite favorable. The fourth point was the size of the training data set that is required within our study for training using 12 input parameters, we estimated that roughly 600 training data proved to be sufficient to reach high R-square values without overfitting. And the last point, in addition to global parameters, it's also possible to predict the local fluid film thickness distribution, which might also be quite interesting to integrate this in multi-body and system simulations. So we hypothesize that in the future this might bring really added value for higher level simulations and to actual engineering system design processes. That's all from my side. Again, thank you very much for having me in this webinar, Norbert, Michael, and Martina. And thanks for every single one of you in the audience for joining. I appreciate it. And yeah, I'll be happy to answer your questions.
Yes, thank you very, very much for that very, very interesting talk. And, yeah. Also a short welcome to Martina, who has joined us now. And then, yeah, the question is, are there questions in the chat?
There are none so far.
Okay. Anyone in the Zoom conference have a question?
Well, I might have a small curiosity. Sorry I joined late. Thank you very much for giving the talk, and hello to everyone who are still here. Well, it's very impressive work, very nice talk. I was curious about the last part. Actually, I was curious about the infrastructure in the last part that you were mentioning, where you were comparing computational time for this kind of workflow. So I'm wondering, this computational time is based on a single machine that you use, for which you can do the whole thing and you can store the whole thing. How is it set? How is the setup for a standard?
Yeah, basically, well, basically the calculation or the simulation is computationally not overly expensive. So basically, you can run this on like simple workstations. And what we do is because for training the artificial neural network, we exported all the data that we had in the FEM model. Basically, we had the lubricant gap, but also as a function of the contact length parameter, like locally resolved. And basically, we only took every 10th parameter to train the ANN model. But when we query, basically everything from the ANN models has been implemented in MATLAB using the machine learning interface. And basically, there we can query any kind of position of the lubricant gap and predict the behavior. So what we did is we queried the same discretization from the neural network as we had from the FEM to have a fair comparison, so that we basically in the end end up with the same amount of data points that we predict. And basically we just ran both approaches on the same computer after each other without any other process, and track the computational time. The interesting part, we had like also these 19 seconds, that does not sound very much, because it's a very simple case of an infinite 2D line contact. So basically we have only basically only one dimension in contact or in fluid flow direction. It sounds not very much, but we're approaching a couple of minutes, maybe 7 minutes, if we already calculate a 3D point contact. While we don't expect any further increase in the already pre-trained ANN prediction. So here we have to differentiate in between the training of the ANN, which is also not very long, but in a couple, like in the order of a couple of minutes, and on the other hand, like only querying the ANN for a result that, like the ANN that was previously trained. And then we're getting pretty fast, and that makes it attractive to actually replace the proximity equations that have been around for quite some years.
Cool, thank you.
That did answer the question.
Yeah. Thanks.
Yeah, I actually have a question into a similar direction, which, I mean, first of all, so we are using either the proximity equations, as you call it, or we are solving like Hapchi, or you are doing the finite element problem, or we are using multi-grid code to run the simulation and then get our contact solution. So if, I mean, just from a practical point of view, like if I look at the proximity equations, they can be written into a paper and I can publish them. If I come with my neural network, how would this be made available to everyone? And can I don't have any experience in the neural network world. I mean, is it just like, can I just save the trained brain somewhere and then use it? So I mean, like you do the training and I just use it, or as end user somewhere?
Basically yes. So basically we would be able to provide any kind of pre-trained ANN that you can simply run. So that is possible. Actually, we're currently working with the Tribonet platform to provide it online. We just have to add some more explanations, and also because we had the comments in German, and we're converting it now into English, and then we want to make it publicly available. Yeah, in that sense, we also have to, or I also have to mention maybe that surely, like the MATLAB toolboxes, they're quite nice to because they're quite easy going and you can get started pretty quickly. But surely maybe it might not be the most efficient language, and might also not fit to incorporate the model into any other kind of software. So basically, it would also be possible to use, for example, the data set that we created to train other models, for example, Python or whatever, which could then be maybe better incorporated into any software in mind. So basically, that's all also there. But the training of the ANN itself, it's not the very critical part. Because it's also very quickly done. So we're talking about a couple of minutes to train the ANN with the input data, and then we just vary the basically the configuration or the architecture. The tricky part is the generation of the database, because you want to have a lot of converged data points in your database. You want to somehow maximize the validity range without changing anything in the model, because on the one hand, for example, if you're in a very low load, or in the let's say the very rigid isoviscous regime, you have other effects dominating. You might, for example, play around with the stabilization of your numerical model, maybe the discretization, to have conversion solutions there, which might influence on the other end maybe the results. So basically, the challenge for us at the beginning was, which took probably 70% of the time of this project, to find a setup for the FEM model that allows us to generate the database in a wide area without changing any configuration of the FEM model. So that was also the kind of the challenge.
Yeah, that's good. I have two more very short. I mean, the one is maybe not that short, but the first one is, as someone who has been studying fluid rheology, so that's always challenging. Of course, you are kind of tied up in your approach, quite tied to this finite element model, right? And I mean, we all know that there's this never-ending fight between, be it Beer-Weiner, Spikes, Imperial College, somebody saying Newtonian is good enough, the next one saying I use Eyring or Caro or whatever equation. So yeah, I guess there's still quite a bit of uncertainty coming there. But my real question is actually, so when you showed the regression parameter of the neural network for for all the input parameters, and then compared that to the dimensionless number groups, I was quite surprised that you said they don't fit that well. And do you think that actually, I mean, we have been using the non-dimensional groups because we always thought they kind of, they signify similarity in a way that we have deduced the number groups from a physical interaction of parameters, so that's why they give us the similarity.
Yeah.
But do you think we can use this method also to actually study such assumptions and think about whether
Yes.
maybe our non-dimensionalist group are not physically based or not fully physically
Yeah.
based?
Definitely. So, but at first, maybe I have to clarify because there's a point. Maybe this was a weakness in that study that we have now also already tackled. What we did is we used the non-dimensional parameters. So instead of having 12 parameters, we only used 3, or in this case 2 parameters as an input to train the model, and to get basically 2 output models. But what the problem was that we used non-dimensional inputs to predict dimensional output. And there you have like this cannot be transformed directly, because we transformed, or basically we predicted the dimensional minimum film thickness instead of the non-dimensional film thickness. So basically this problem, meanwhile we found out will be solved to some kind. And you're getting also better results when you employ these methods. Basically, what you have to do is you just have to multiply in basically the radius. Basically, we could do it with the same database we already had. So that's the one point. Still, the non-dimensional groups, they have been established for various, let's say, decades, and have been very widely employed. But still, I believe that one interesting aspect of ANNs can also, or machine learning in general, can be to study the influence of the several or the different parameters, maybe come up with new non-dimensional groups if that's possible, and also to study or tackle exactly that issue of fluid rheology, to see, okay, which parameters actually do we need to predict the film thickness, and which parameters we might omit in the prediction, and also to widen it up. Of course, in our case, we had rheological models in our FEM simulation that are part of the database. If we open it up, because as you said correctly, like there's always this discussion going on about the different approaches, about the different rheological models. In the end, someone will find or formulate a new lubricant that will behave differently, and then like all the prediction accuracy of the models would begin, which of course also holds true for the non-dimensional or the proximity equation. But still, it can maybe be used to find more generalized ways of predicting film thickness with, not taking into account these classical rheological mathematical formulations. But that's one of the aspects we want to tackle in the future as well.
Very, very good. Very, very interesting. Thank you very much. So then I would say we don't have any other questions in the chat or in the group, I think. As that is not the case, I would first of all like to thank all our speakers of today's session. Once again, thank you for taking the time to share with us what you are doing, to talk so openly about your results. And of course, I want to thank my co-organizers, Martina and Michael, of course, for putting in so much work. And then I would say, we hope that in the next year there can be another tribology seminar series, and we can continue with some interesting topic.
Yes, absolutely. Thank you, everyone. Thank you for giving the time and the space. It was a pleasure to organize this. Also, thanks to Norbert and Michael.
Yeah, thanks Martina, thanks Norbert. Thanks to all the speakers, thanks to all the speakers of all sessions.
Yes,
and
absolutely.
to the YouTube viewers that maybe have not caught the first 2 sessions, they are on our channel. You can find them pretty easily, especially if you already found this video. And they will be updated shortly with correct timestamps, because now the timestamps correspond to the to the actual CET time and not to the time in the video, but this will be fixed very shortly. Okay.
Perfect. And with that, all I wish all a nice weekend, and I'd say we close this session. Thank you all.
Have a good weekend, everyone. Bye.
Goodbye.
Thank you. Bye. Goodbye.
Ciao.